Hello, everyone. This is the first lesson of the next unit, which is on dynamics. Still part of the motion unit, but now we're going to be focusing on forces that are causing motions. So I'm going to start out looking at types of forces, and then I'll come back and reveal the secret word here. So often I'll start in class just saying, list as many words you can come up with to do with forces. So people usually start with things like pushes and pulls and slaps and whatever, and then they start to get a little more specific. They might say something like gravitational force, or gravity force, or all sorts of different words come up when you ask a group of people to list as many words as you can do with forces. So it might look something like this typically, right? So push, pull, and then someone says magnetic force, and then someone else is like, oh, electric force. I remember when I rubbed a balloon on my head and stuck to the wall. And then back to more simple things like wind force, force of water, going over a dam. Someone at one point said the force, Star Wars fan. I almost said Star Trek fan. Oh, Star Wars fans be mad at me out there. I always do that on purpose, actually. It's just a joke. Gravity force, mechanical forces, and so on, right? If you're looking at which ones of those are fundamental forces, gravity force, electric force, and magnetic force, electric and magnetic are double part of the same, so double circle there. So gravity force, and then the electromagnetic force, and then there's actually two others. There's 4 fundamental forces of nature, and so they are, reveal this information here, but the strong nuclear force and the weak nuclear force. So the electromagnetic and the gravity are actually the weakest forces. Gravity is the weakest by far. Easy demo for that is show that a magnet can pick up a nail against the force of gravity of the entire Earth, right? Even with all that mass of the Earth, a little wee magnet can pick up a nail and win that tug of war force. So the strong nuclear force is the force that holds nuclei together. And then weak nuclear force is to do with radiation and nuclear decay. This strong nuclear force is something I wish more people asked about, thought about, talked about, asked about in the student front, thought about and taught about as well, included in classes. So science teachers out there really should mention this in the context of talking about the structure, the model of the atom. So we talk about how we have positives in the nucleus and the electrons attract to the center because opposites attract, right? Everybody says that, but I don't know anybody that has mentioned in their classes, why the protons don't repel apart. We know that likes repel, right? Well, the reason they don't repel apart is because of the strong nuclear force. So in chemistry, I always talk about how atoms are formed in cores of large suns and supernovas and things like that, where protons get pushed together to the point where they actually start to get held together by the strong nuclear force. The range of the strong nuclear force is decimal 0.00014 zeros, and then a 1 for meters. Okay, so it's called femtometers, 10 to the negative 14, which not coincidentally is the average size of an atom's nucleus, right? Because the strong nuclear force doesn't hold on to protons beyond that, so they just repel away. So the strong nuclear force helps hold them together. The neutrons are there to help hold together as well. That's why you can have different varieties. So a little bit of chemistry talk going on, but the physics behind some of it is neat to talk about. So, if you add the strong nuclear force and the weak nuclear force to the list, it's a more complete list, right? So those are your types of forces. So explain, I should mention here that these strong, weak, electromagnetic, and gravity, those are all like non-contact forces, right? Those are action at a distance forces. And their forces are transmitted by exchange particles. And so with the electromagnetic force, it's actually the photon. With the strong nuclear force, it's a particle called a gluon. And weak nuclear force, it's bosons or vector bosons, I think they're called. It's very specific, right? Gravity, they theorize that if it has an exchange particle, it would be the graviton. They called it, like if it has one, they call it the graviton. They've done lots of experiments that they feel should identify a graviton if it exists, and they haven't been able to find one. And I think there's a good reason for that. And we'll talk about it later in the course. But I'll be showing you reasons why a lot of scientists say that gravity isn't actually a real force. It's actually just curvature of space-time that we're experiencing. So that's probably a pretty controversial thing to say. And you know, like, wait, what? Did you just say gravity's not a real force? But we'll dive into it later on. Either this course or grade 12, I forget. So moving on with this topic here, there's a very important concept for this new unit on forces. And so I'm going to be showing you a bunch of demonstrations, videos of them, magic ring, block and a stick, the ratchet end of that can bend, apple knife and hammer, card flick. There's all sorts. Okay, so I'll be showing you all these things. So to get started with, this is my magic spinning ring, and so I'll show you what it does, the magic of it. There's a little video. And if you restart the video, you'll see that it is with the stone down as I start to spin it. So right away, I can't even pause it quick enough. Somewhere along the way, you see like the stone is down. I'm trying to get a clear picture there for you. That's the clearest I've got at the start of the video. So stone is on the counter, like a balancing point. So think about picture here. No, it's got this end down on the counter. I'm attempting to spin it balanced on that stone. And if you watch the video, you'll see that right away it jumps up to the top. So I actually recognized this in grade 10 French class in Sault Ste. Marie. I was bored and I was spinning my ring, and I noticed it was always flipping up, and I was curious about it. So I guess I was curious about physics concepts at a young age. Here is a slow motion replay of this craziness. My LEDs in my kitchen are flickering away, 60 hertz. There it is. All right, you can see clearly it's stone side down, spin going, right away it like whoop, flips up. I am not good at magic tricks, but this one always works. All right, question is why? It's to do with this lesson. Okay, that one's a little harder to explain, but some of them have become more obvious, right? But why does it always flip so the larger mass is at the top? There's a video from Veritasium. This guy's amazing, Derek Muller. I'm just going to let you play those later if you want to watch them, but it's basically same idea. You spin this thing, and you spin it with the heavy part at the bottom. So spin it so that it is oriented like this, the hole at the top. Spin it, it'll flip up and end up the other way around. Group clone here. So you spin it like that, and before long, it's sitting there spinning like this, spinning round and round. Okay. There are explanations in the videos as well. Later on, after having played with my ring all those days in high school, I found this tippy top. I'll play the tippy top video. Find it easily enough here. So how a tippy top works, I just want the tippy top, the spinning top flips over. So tippy top, spinning top. So it's a little like mushroom shaped looking thing.
We have the tippy top. It's a spinning top that will invert during its spin.
So you try to spin it with the bottom like that, and just basically he's going to give it a spin.
I'm just spinning it very slowly at the moment because you can stop it fast now, so you can see what happens. You'll see that actually when it's very, very fast.
That's the magic of that one. So it does the same. It has a harder time flipping up.
So we do it properly fast now, so you can see what happens. You'll see that actually when it's very, very fast. You can see there the actual tippy top being.
So again, why does it do that? And again, it's to do with an important concept that we are trying to identify for this unit. And so here's me on my back deck during COVID, teaching from home here. And so I have a sledgehammer, and I'm asking the students if it's easier to balance with the heavy part at the bottom or with the heavy part at the top. Okay, so basically think about it, pause the video, talk about it, and so on, right? And so I try my best to balance it with the heavy part at the bottom, just with one finger on it. And that's the best I could do. Very stable. And I actually just sort of let it go there and then say, okay, question is why? Why does it balance easier like that? And this one's easier to answer in terms of the concept we're trying to identify. My ratchet end hammer, or a ratchet end with hammer, I should say, or whatever. So this is a ratcheting wrench, but it also has the flex end on it. Okay. So flex is like that. And if you tap the wrench right there, what happens? A lot of people would think, oh, you're hitting the ratchet down, and so the end's going to fling down. But watch what happens, little taps. Okay, that end rises up, which seems counterintuitive to a lot of people. They wouldn't expect it to rise up like that. Again, the question is why? What's the concept we're identifying, right? Apple knife and hammer. A whole bunch for this. Okay, so my kitchen here during COVID again. So what happens if I tap the knife? Is it going to send the apple flying? A lot of people think it would. Let's see what happens. I find it easier if I just do those little hits rather than a big one, because it just kind of dangerous. But see, it's just slicing through, right? So why does that happen? The coin flick, so Newton's bottle, I have somewhere here, I think. So Newton's bottle. I closed it before. This is a version of something else that another video will show, but so a bunch of coins on top of a bottle, and then you hit the paper and it yanks it out really quick, and the coins stay there. Question is why, of course, always along the way here. This one's neat too, the ring and bottle. Ring and bottle. There we go. So ring and bottle. Boom, you can pull it, the ring out, the coin just drops right into the bottle. Even if you have a bunch of nuts and bolts, I guess this is nuts, drops right in. Again, what's the concept to do with that, and so on and so on. What else do I have? The card flick. Card flick. Probably should have shown first. Card flick, coin drop. So cut speed up here to flick, and the card goes away. Right? There we go. Card zips away, and the coins stay behind and fall into the cup or the glass. And there's just almost an unlimited supply of these. So what do all of these videos have in common? What's the driving principle behind them? We can go back and talk about it a bit more in each one. Hopefully you are noticing or getting along the way here, and you might even have noticed actually one of these had the name in it. It's inertia. Okay. So dictionary definition of inertia, tendency to do nothing or remain unchanged, is a terrible definition. Property matter by which it continues in its existing state of rest or uniform motion in a straight line unless it's changed by an external force. Much, much better definition. Okay. I had it backwards here. Tablecloth trick's a classic one. So tablecloth trick. I thought I got away without ads on that one. Let's go back to tablecloth trick. videos. Tablecloth. It's this one here. So here's a physics teacher getting cheered on by his class. It's always a fun moment.
All right, somebody help me now.
And the crowd goes wild because physics is fun. It's interesting stuff. I don't know if I can get away with this, playing this one or not. Newton's third law. I forgot I even had this video. I just found it. So Jay is trying to trying to sabotage his son. You watch Modern Family, and so he says, "Oh, I want you to do a magic trick for these people," hoping it's going to fail badly, right? So here's Phil going to do a magic trick.
Our money disappeared. Oh, hold on. Congressman Morley, enough with the taxes. You don't see us making you pay through the note. Okay, hold on. Nobody move. I got this.
So he tried to sabotage him. Didn't work. And then this is an amazing video. So this was a video that was out for a while. So this video was hitting the internet, right? And of course, people sent it to MythBusters and said, is this real? Is this even possible? Like, they're basically wanting them to bust it because clearly it's not possible. And so the found this video as MythBusters for the impatient.
Check this out.
I hate to break it to you, but I've seen that before. It's a magic trick. It's not a myth.
This isn't, but there's a video that's been making the rounds on the web that is a twist.
So I'm just going to jump a little bit through. He talks about that one, of course, right? And then here's them trying it. as expected, right? But then they go next level. They've got like, I don't know, whatever it is, like 400 feet of line. And, so he's going to be going like 120 miles an hour or something by the time it actually pulls the cloth.
2, 1, go!
Pretty close, right? Like they managed to almost do it, but still, busted. It's not quite the same as the myth. And then they fake it, right? The way they did with the sheet of plastic and so on.
Should, in theory, slip out easy as you please without disturbing anything on the table. That's how I think they did it. This is tablecloth full, the sheet. 3, 2, 1, go!
Boom. So the idea, of course, is all of those dishes and so on have inertia, right? And so they want to stay put, right? All of the cases, the dishes have inertia, and so basically, in order to accelerate them sideways, there has to be a force on them, and it has to have time to get them moving, and so on. All the Newton's laws are going to kick in. But for now, we're just basically saying like they're not going to move unless they're made to move by a force, and that's the connection. I'm going back to the ring. Basically, it's most stable when the mass is at the top. Maybe I'll go to the sledgehammer first, actually. So the sledgehammer balancing trick here, it's most stable when the mass is at the top. Just hang on 1 second. All right, okay, sorry about that. So what this has to do with inertia, it ends up being easier to balance it with all of the mass at the top, because that means the top wants to stay still. And so it's easy to move the bottom to keep the bottom below the top. And that's, of course, what you do to balance something, right? Versus the first way I tried to balance it, the top is it moves super easily because it doesn't have much mass. The bottom's harder to move because it does have a lot of mass. And so it works against trying to balance things. And so in this situation, you can think of that as, I like to think of it at least as, it's more in balance. It's more stable with the mass at the top. And so any little vibration, especially with this one, you saw like when it hit the side, it started flopping around and it just goes to all sorts of different states. It ends up stuck in that most balanced state. And it's most balanced, because of the inertia, when the object is at the top, the inertia helps keep it there. The bottom tends to stay underneath it because the bottom, because the top stays still, I guess you should say, right? And the hammer, when I'm tapping here, this end has inertia, and so it stays put. The wrench gets hit down, but this end's free to stay put because it's on a flex end, right? So that's why it goes up a little bit each time you hit it. With the apple, I'm hitting the knife, but the apple has lots of inertia, so it wants to stay put. So the knife jabs sideways, but the apple tries to stay put because it has inertia. The coins have inertia, so even though you yank the money out, it takes a fair bit of force and time to accelerate the coins sideways, right? So they tend to stay put. Same with these guys. The nuts on top here tend to stay put unless if you gradually pulled the ring sideways, then you'd be able to get the nuts to come with you. But since it goes so fast, there isn't time for the friction force that's here to sort of pull and get them moving, right? So they have inertia, they stay put, and they fall in the bottle. Same for this one, same for everything we've done so far after that, okay? So the inertia, objects with mass resist changes in their motion. If you have more mass, you have more inertia, right? And so we know a force is needed to change the motion. That's the big aspect of this section. We're talking about forces. And so objects that are stopped, you might want to extend this, right? The dictionary one is pretty good, right? It's state of rest or uniform motion, and it stays in a straight line too because it takes forces to turn corners. So if there's forces, then you'll turn corners or you'll speed up or slow down. If not, you won't. Okay. So objects that are stopped stay stopped unless a force acts on them, and objects that are moving stay moving in exactly that same motion, right? This one, of course, the objects stay moving. Objects staying stopped unless a force acts on them is really obvious. Very easy for people in history to have known that one. The fact that objects stay moving is a lot harder to believe, I guess, just because of friction. And so, friction is that force that's causing the deceleration, I'm saying in air quotes, but it is correct in that context, right? The negative acceleration, if you have velocity forward, causing you to slow down. So more inertia demos, some that you've seen recently in TikTok world and stuff like that. So give the people what they want. Leaves on trampoline. It's on trampoline. I think I moved it already, but where is it? Video lessons, video tab. Still in my video tab. Sorry for this. I might pause if I don't find it right away here. I'll just pause quick so I find where I've hidden the file. All right, leaves on a trampoline. There's a compilation video of this kind of stuff. Person coming down here, they're going to hit the trampoline mesh here and force it to go down really quickly. The leaves don't change their velocity that quickly. They have inertia, right? So it takes a little while for gravity to pull on them, bring them down. Just looks neat, right? So that, along with I remember my daughter showing me these recently, so I know it's something that's out there for sure. The clay on the tennis racket, part of that same video. Tennis ball comes down and boom. Clay takes a little while to fall due to gravity, the tennis racket went much quicker because it was hit by the tennis ball. What else here? 7 inertia demos. That's what I kept finding when I was typing this in. I think some of these are probably repeats, to be honest. Let's see here. Yeah, there's the ring. There's the flick, card flick. Yeah, I would have just flicked it instead. There's the tablecloth trick, basically, just the wimpy version. The knife, the chair. Yeah. So this coming along here. Textbooks were coming in, moving, and so the chair stopped all of a sudden, but the textbooks didn't, of course, because they have inertia and so on. Here's the egg. Hit the plate out really quickly, and the egg stays behind. Right? The high risk one. I put the egg on your face, literally. Cool inertia videos. Everybody likes cool videos. Is there cool inertia videos? I think I'll just, at this point, cool inertia. Yeah, let's just move on with life here. All right, so true or false? An object in motion will slow down unless it's acted on by an unbalanced force in the direction of motion. Object in motion will slow down unless it's acted on by an unbalanced force in the direction of motion. Sort of true, right? Because of friction, but really, in reality, friction is a force, right? And so the answer is actually false, because friction is actually the one that's slowing it down. It is a force on it. So if there's no friction, that is a false statement. You can stay at a uniform motion with an applied force to balance friction, and we'll talk about that later in this unit, of course. An object at rest will stay at rest unless acted on by an unbalanced force. That is true. An object in motion will remain at its speed and direction forever unless it's acted on by an unbalanced force. That is also true. Okay, so why do we have to be so careful in talking about this? Why is it so misleading and confusing? Why do people tend to come to the wrong conclusions about this? You see around you that moving things are observed to come to a stop unless you keep pushing on them, right? Galileo worked super hard to help people understand that friction was the cause of that observation. So his thought experiment was like this: drop a ball and it's going to go to about the same height. Drop a ball, it's going to go to about the same height-ish, and so on. So he's like, well, what would happen then? And basically the ball could go forever trying to get back to that same height if it wasn't for friction. Okay. So this is a Galileo marble track, same idea, right? You drop the ball from here and it goes to that same height. And so if you'd had multiple tracks of this, the ball would go this far, and then the ball would go this far, and the ball would go, and so on. Okay? So nothing major there. So this is known as Newton's first law. Okay? It's the first main thing you have to kind of get under control and talk about in order to work your way through the effect of forces on things. You have to understand that objects have inertia. You have to push on them to accelerate them. Right? So Newton's first law is that every object continues in its state of rest or uniform motion in a straight line unless acted on by, and usually people would say, an external unbalanced force. So, not external. I'll type in and see if I can have any better luck finding my videos here. Not external. So a funny video of someone, and it's a silly video, but like this vehicle's stuck. They're trying to push it out. This guy's pushing on the roll cage here, the headache rack they call it sometimes in the States. He's inside the truck. Like, that's not an external force. That's not doing anything, but the guy's pushing with all his might. How embarrassing. I don't know if it's a joke or not because I don't understand the language they're speaking, but it's embarrassing if they actually thought that was the case, right? So same deal here. You ever felt like your brain is inadequate? Just imagine being this guy trying to push on the truck from within inside the truck. Like, just doesn't make any sense, of course, right? So yeah, don't do that. Video temp is where this next one is. This is a commercial that I managed to find. I kept describing to students, you ever seen that Kraft Dinner commercial? Analyze the physics of this one. He's enjoying his craft dinner, the cheesy goodness, and then his rodent that likes cheese.
Gotta be KD.
Right? His rodent that likes cheese is pushing on the aquarium here to try and get to the cheese. Obviously not possible because the hamster or whatever that thing is isn't managing to push externally. It's just a force within the aquarium. Obviously not going to work, right? So it's just a silly picture. My story I tell in class is like driving by a candy store, and my dad wouldn't turn to go into the candy store, and so I reached over and pushed on the door, and all of a sudden the car was screeching into the. I was just that strong, as a joke, of course, right? But not possible because it's not internal forces, or not external forces, I should say. And there is this, unfortunately, this viral video going around. So umbrella, maybe I'll just type in. Yeah, whether it's probably in the downloads. Just downloaded it recently. Yeah. So oh boy, loud. So this is either a trick, or it's a downhill, or there's something wrong here, because it doesn't have an external force. Now there is a possibility of the wind from the leaf blower scooping and pushing, like, and turning and pushing back. That's possible. But if all of the energy is getting absorbed there and there's nothing thrusting backwards, picture he'd be feeling the pull of the umbrella forward, but he'd be feeling the push of the leaf blower back. And we'll come back and talk about that. But basically, I just started to show it just to get you thinking about it. And we'll analyze it further later. But basically, there aren't any external forces. Normally, you'd take your foot and you put it down on the ground and you push, and that'd be your external force that helps accelerate you forward, of course, right? That's how skateboards work. So this idea of this external unbalanced force, think of this tug of war here, right? And they're all internal forces it balances. If they're balanced, they remain stationary. If you have constant velocity, while you're managing to lift something or whatever, don't confuse motion with force, though. Okay, if we're going with constant velocity, you'll see later on in the course that means there is a net force of 0. If you're speeding up, that's when there's a net force. Okay, we'll talk about net forces soon. Net force just means all of the forces added up. All right, so just a heads up for that later on. We don't want to confuse the fact that there is motion with there being force because of this. Right? Objects remain in their state of motion unless they're acted on by a force. It's the opposite. Right? But it seems not the case because of friction. One of those inspirational posters, inertia. Your truck has brakes, but the massive stone in the back does not. So the truck stopped really fast, and the stone was moving, and it had inertia, and so it stayed moving, and not so good. Person who owns a truck, not too happy, I'm sure. This is another neat demo. So this guy, Steve Mould, I believe his name is. He has a YouTube channel, and so he put out this video a while back of these self-siphoning beads. I'll play the video. You might have seen it on some kind of TikTok or something like that. Just one sec here. All right, so here. One. Yes, okay, just had to double check. Here's the video, Steve Mould, some YouTuber, shows. Let's just keep going here, whatever. It's just got these beads that you use for like pulling on lamp cords and stuff like that. He shows this like weird kind of phenomenon that he noticed, and he analyzed it, and he, basically brought it to light, and people hadn't really thought about it before. And so he actually has the process named. It's called the Mould effect now. It's actually named after him, right? Like Newton's law is named after Isaac Newton. He has the Mould effect named after him from his YouTube channel. He just discovered he's like a science guy on YouTube, right? So falling beads. I'll show you my version here. Falling beads, regular speed. Oh, actually, I don't want zoom. I want just regular, I think. Maybe that'll go. That's just outside the math office at Rideau. So there's times in that when you end up with this height here. And the explanation, there's lots of explanations to do with this, but the one explanation that makes sense right away to talk about is as these beads are going up, right, they end up with inertia. And so it takes a little while for the forces to act to change the direction from up, right? That upwards velocity there means that they have inertia. That's the motion they have, right? There's actually other words for this, of momentum and so on, but they have inertia, and so they're going to keep that motion. And so they're going to be hard to turn around, and that's why they actually sort of climb up out of the glass like that, which is just kind of weird. Okay, but it's an inertia, another inertia link. So these ones aren't as calculation based. You probably should find those a bit of a relief in terms of how they are just knowledge questions. All right, so give those a try. Let me know if you need any help. And that's all for now. Thanks for watching.